Hello, today I'm going to go over a couple of questions from homework number 5, generally relating to limits or continuity. So I'm going to start off with number 27. So this one is a basic limit, and you want to start off like you do with a lot of limits by just plugging in the x value they give you, which is infinity. So x times x as x approaches infinity is just infinity, and sine of 1 over x as x approaches infinity, 1 over x is going to turn into 0, so you're going to get sine of 0 or just 0. So if you just plug it in, you're going to get infinity times 0, and that is an indeterminate form. But it's not one of the good indeterminate forms. When we're dealing with limits, you always want everything to be in the form of 0 over 0 or infinity over infinity, because that way you're going to be able to apply the L'Hopital's rule, which is going to make these problems a lot easier to solve. So we're going to take the original and manipulate it a little bit so that it is one of these forms. And we'll do that by leaving sine of 1 over x, except taking x and putting it on the bottom as 1 over x, which is the exact same function as before. So now you take the derivative of the top, since all of this is going to be 0 over 0. You can plug that in quick. But you're going to take the derivative of the top, and with a little bit of chain rule, that'll be cosine of 1 over x times negative 1 over x squared. And the bottom, same thing, negative 1 over x squared. Also, that's the limit. Whoops. And what's great about this is you can now cross out the negative 1 over x squared, and you'll just have limit as x approaches infinity of cosine 1 over x. Now, if you plug in infinity, as x approaches infinity, 1 over x is going to approach 0, so all of this turns into cosine of 0 or just 1. And that is E. All right, pretty simple. Now moving on to number 31, which is a little bit more complicated. So the first thing you're going to want to do is this entire function is defined almost exactly the same at every point, except for these two specific exact values that are sort of thrown in there too. So to start, we should just factor out what we have at the top. So I'll take f of x equals 3x, x minus 1, over, in this bottom section, a little bit of factoring magic, it's going to be x minus 1 times x minus 2. And what's good is you can cancel these two out. So at most values, it's going to be 3x over x minus 2. Now, first things first, this x minus 2 should give a little bit of alarm bells, because that is going to be a vertical asymptote. Unless it cancels out with something, as x approaches 2, either from the right or the left, the values of f of x are going to get really, really large. So if you imagine that graphically, at x equals 2, the function is going to do this or this. So, make that a little bit prettier. It's going to do something like that. And what's important there is if you take the limit as x approaches 2 of f of x, since it's shooting off to infinity, you know right away that that limit does not exist. And if you remember, one of the basic criteria for a function to be continuous at a point is that the limit has to exist at that point. So right away, you can say that it's not continuous at 2. And then you can knock out this one and this one. Now, from there, you want to look at this x minus 1. Since we crossed it out, this function applies to every value except x equals 1. And at x equals 1, you're going to have a removable discontinuity. And the way you check for continuity there is you're going to want to take the limit of this top function and compare it to this. So and take the limit as x approaches 1, because 1's what we're looking for, of 3x, x minus 1 over x minus 1, x minus 2. Since you're here, you can just cross out x minus 1, and you're going to get that the limit equals, just plug in 1, 3 over negative 1, negative 3. Then you compare this with the actual value, which is negative 3, and it equals that. So if the limit equals the actual value of the function, that's the criteria for it to be continuous there. So it is continuous at x equals 1. So it's continuous everywhere except at x equals 2, meaning that B is correct. And you can knock out all the other ones by various different means. Then, moving on to 32. This one, yet again, you want to see this and immediately think factoring, since you can take it and factor out the bottom by difference of perfect squares, so 4 over x minus 1, x plus 1. And like we were talking about before, both of these are going to correspond to a vertical asymptote, because if you get really close to either of these numbers, then the denominator of the function is going to be really small, which means the function itself is going to get really large and it's going to tend toward infinity, and you'll get one of these things, vertical asymptote. So right away, you know both of these values at x equals plus or minus 1 are going to correspond to vertical asymptotes. But the question is also asking about horizontal asymptotes, and luckily this function does in fact have a horizontal asymptote, because if you look at it, I'll write it down here. You look at the exponent of the leading coefficients, you can imagine this 4 having an x to the 0th term next to it, and you want to compare those leading coefficients. The x to the 0 is less than x squared, so you consider this one of the bottom-heavy questions. And if it's bottom-heavy, then the limit as x approaches infinity of f of x is going to equal 0. Or in other words, there's a horizontal asymptote at y equals 0. So you can look at the questions, you can look at the various answers. One vertical asymptote, no. Y-axis is vertical asymptote, no. X-axis as horizontal, and x equals plus or minus 1 as vertical asymptotes, yes. And same thing for these ones, you can rule them out pretty quickly. All right, now moving on to the last question. Now, before you get started on this question, the most important thing to recognize is if you're taking the limit as x approaches 0 of something, you'll notice, if I'll rewrite it quick, the immediate thing that value is going to hit, the first thing that happens to it is you're taking the reciprocal. So remember, when you're taking the limit of something, you're looking for the limit both from the left and from the right. And the limit as x approaches 0 of 1 over x from the left is going to be negative infinity. And from the right, it's going to be positive infinity. So when you see this, immediately you should think that you want to separate it, because those are going to be very different values if you plug them in. So we'll split it up to limit as x approaches 0 from the right of 1 over 2 plus 10 to the 1 over x, and limit as x approaches 0 from the left of 1 over 2 plus 10 to the 1 over x. We'll figure out this first one. 1 over 2 plus 10, and the power, it'll be 0. If you take 1 over 0 as 0 approaches 1 over 0, since you're approaching it from the right, it's going to get infinitely high, and you'll have positive infinity. So 1 over 2 plus 10 to the infinity, which equals 1 over 2 plus infinity, which of course is going to equal 1 over infinity, and that is going to tend towards 0. So the right branch will approach 0. The left branch, 1 over 2 plus 10, and this time it's going to be negative infinity since you're approaching it from the left. And so you'll have 1 over 2, and 10 to the negative infinity, it's going to get closer and closer to 0, so you'll have plus 0, and the left branch is going to be 1 over 2. So if the limit from the left does not equal the limit from the right, then you can say confidently that the limit does not exist for the function. And that would give you E. That covers all the questions that people had issues with. Hopefully that's helpful enough, and let me know if there are any other questions.